Thank you very much for attending this talk. I'm Tao Chen from Loughborough University, UK. Today I'm going to talk about our work on lifelong dynamic optimization for self-adaptive systems, where we formulate a new formulations and the corresponding solutions to planning a runtime adaptation for software systems. So, the motivation of this research is that many software systems come with different configuration options, and they can be changed at deployment time or at runtime. As you can see here, there are a few examples of the number of configurations, and there are quite a lot, so it's very difficult to manually inspect and do the right configurations. Finding the best configuration beforehand is extremely hard, especially in considering the fact that environments, for example, workload or job times, the system encounter can be uncertain and they always change when the system is running. And this is an example of Apache Stone where it experienced two different environments of the workload. And two things we can observe here. Firstly, the default configurations perform very bad, as you can see on the green line here. And secondly, the global optimal configuration in one environment may not be the global optimal when it turns into another environment. For example, the blue light here. So what we are doing in this work is that we try to treat a highly configurable system as a self-adaptive systems for SAS. Therefore, their adaptation plan can be changed at runtime in reaction to environmental changes. We are particularly interested in optimizing and guaranteeing certain performance concerns such as latency and throughput. So essentially, we are facing SAS planning problems. What is the next best adaptation plan under changing environments? But for the SAS planning problem, there are a few challenges. For example, as we have shown, the number of possible adaptation plans can be high and the measurements are expensive. There also could be interactions between different options. And as we can see here, the configuration landscape and it's rugged and sparse, and they may contain many local optimal. As we can see here, the little dot here is the global optimals, and the very stars representing the peaks are local optimal. And local optimal, we mean those adaptation plan that it's always better than the surrounding neighbor, but they could be suboptimal, and some of them are actually very bad, if you can see here. So in current work, there are two kinds of planners. One is stationary planners, where there's a new planning conduct on each timestamp or environments. And also there's a pseudodynamic planning where it make use some randomly generated plan from previous rounds. But the problem with this is that the true dynamic has not been explicitly handled during the planning phase. So as a contribution in this work, we follow the definition of dynamic optimizations and we formulate the SAS planning as a multimodal optimization problem. And to be lifelong, we allow the planning to run forever and it's stopped only when the system is taken offline. And to be dynamic, we design a planner that explicitly takes into account the change as time goes by. So to do that, we propose the leaders. It's a framework to address the above, and we basically do two things. Firstly, we refine a model objectivization model, MMO, an optimization model to fit our context based on our needs and observations. And secondly, we design an architecture that based on hierarchical feedback loop for the runtime adaptations. So all of our design were derived from our observations of the highly configurable SAS, and we observed three different characteristics. Firstly, highly configurable systems often come with multimodal landscape. That means they have many local optimal as we have shown. And secondly, the overall multimodal probability is still preserved under changing environments, and there are many shared local optimal. If you can see on the two figures below, they are representing the landscape for two different environments, and we see that the peaks are actually quite similar across the cases. And the final characteristic is that the global optimal in one environment is likely to become a local optimal in another, as we can see here. The circle represents a global optimal here, but when you change into another environment, it immediately becomes a local optimal. So what does this tell us? And it means that we can formulate the SAS planning by considering dynamics in two goals. Firstly, we try to preserve as many local optimal as possible because they can provide useful information. And secondly, we want to do so without losing the tendency towards finding global optimals. And that's a very typical multimodal optimization problem in a dynamic environment, and we design a multi-objectivization planner for the above goals. Of course, there are many different algorithms for multimodal problems, but they largely compromise the ability to reach the global optimal, which violating goal 2. Instead, we refine MMO model, which is a recently proposed model for configuration systems, and it can be paired with different Pareto optimizer such as NSJ2. So here is a model where it consists of a target performance objective. It's a one that we try to optimize, and an auxiliary performance objective, which is one that we don't care the value about. But it's useful for us to construct a transfer space using the weights. So why does it satisfy a goal 1? Because these artificially created Pareto dominant relationship help us to preserve adaptation plan with very different auxiliary performance objective, and that encourages planning to explore a wide range of search space. And why does it satisfy goal 2? That is because the global optimal of the target performance objective is still Pareto optimals in this case. Therefore, we still preserve the possibility to reach the best one. But we cannot directly apply MMO to our context because in the original model, it needs an additional measure of an additional performance objective, which could be harmful for runtime adaptations. Also, because different performance objectives could have different scales, and that make MMO very sensitive to the weights. And usually it needs some pre-tuning, but that is not possible for our SAS adaptation problems. So what we need is really a new auxiliary objective that is easy to measure with the same scale as the target performance objective, and most importantly, it allows similarly performing adaptation plans on the target. We have very different values on the auxiliary objective. So how we do that? So in each iterations says for each adaptation plan X, we firstly find some neighboring plans within the current populations, and within the neighboring plans we find a plan Y that differs to the target performance objective of X the most, and then we use the target performance values of Y as the auxiliary objective for X. So here's a quick example where we shows for the point 10.2, it has 4 different neighbors. For example, if the point 9.2 has the largest differences to the point 10.2 in terms of the target performance objective, then we immediately set its target performance objective as the auxiliary objective for point 10.2. And that is clearly very easy to measure because no additional measurements is needed, and also it will have the same scale because they are basically the same performance objective. Also, because of this high sparsity, similarly performing target performance objective will likely to have very different auxiliary objective. So this is the architecture of Lidos, and it contains 2 different loops. And the Lidos is actually running as a managing system, and it will control the system being managed. On the outer loop, it's a typical SAS loop where we adopt the managed systems when we reach an measurement interval. So in that case, we won't just adopt too frequently. And what makes it special is that inside the loop, we have an inner loop that runs forever, and it continuously query a cyber twin of the managed systems. In this case, it could be simply another running instance of this managed systems, or it could be simply as a surrogate model. And in terms of experiments, we carry out a test on 3 real-world SAS, each with 2 different environments that can be changed from one and another. And we have a 400 total measurement with adaptation interval of 150, repeat 50 runs. In terms of competitors, we compare with a stationary version of Lidos, where it still uses MMO, but every time it started planning from scratch. And we also compare with SOTA stationary planners and pseudodynamic planners as well. And as far as metric, we use various different statistical tests and effect size to make sure the reliability of the results. So first RQ, we ask how beneficial of being dynamic. So we compare Lidos with its stationary counterparts. As we can see that Lidos perform significantly better in terms of statistical test and also the magnitude of improvements, and is up to 10 times more improvement. That means explicitly considering dynamic in Lidos is generally more beneficial for SAS planning. Secondly, we ask, does Lidos effective compare with the SOTA? And here we use the Scott Note test to rank Lidos and the other two SOTA approach. And here we can see that Lidos consistently being ranked as the first, and there's 5 out of 6 cases where it's only one in the first rank. And in terms of the improvement, it's also significant. If you look at one round of the adaptation plan produced, we see that Lidos try to allocate most of the local optimal, as we can see here, and also compare with the pseudodynamic planner, where it would just allocate one local optimals. Well, they may not to be differ too much in the current environment, but when we change environments, we see that some of the local optimals that Lidos preserve are very promising, but with the pseudodynamic, because you only converge to one local optimals or even random points, then the chances are it may not be that promising. And it's also worth noting that the benefit of Lidos is not because of random sampling. If you compare with the stationary planner on the right, we see that if you just do random sampling, the resulted adaptation plan to start with would not that promising either. So that means Lidos is effective compared with the SOTAs, and also at the same time that's certainly due to the preservations of local optimals as part of the planning process. And finally, we ask, does Lidos efficient compare with the SOTA? And here we firstly measure the number of measurements for the SOTA approach to achieve the best performance. And then we do the same for Lidos to see how many measurements it needs in order to reach the same level. And we calculate the ratio between these two measurements as a speed up. As you can see that Lidos is much more efficient than SOTA planners, achieving up to 5 times or even 10 times speed up over the pseudodynamic and the stationary counterpart respectively. And what is interesting to see is that with the current environment that Lidos may not be largely better than the SOTA, but once the environment change, we can see that the improvement of Lidos is becoming much more obvious, and it's again thanks to the preservation of multiple local optimal and the tendency towards handling dynamics during the SAS planning. Right, so in conclusions, here we introduce framework Lidos that refine an MMO model for planning and fit into architecture with hierarchical feedback loop to achieve lifelong and dynamic optimizations. We carry on experiments on 3 real-world SAS, each with 2 different environments, and compare with different SOTAs. Our results shows that Lidos is more effective, more efficient, and that benefit is indeed attributed to the fact that multiple local optimals can be preserved. So in terms of future work, we show that lifelong dynamic optimization is factual for planning in SAS, and that could excite a few research directions. For example, we can design memory mechanism to more precisely track the details of landscape changes between different environments. Okay, so this is the end of my talk. Thank you very much for attention. I'll be happy for any question in the end of the conference. Thank you.